previous video, I had discussed Euclidean domain, unique factorization domain, principal ideal domain, integral domain, maximal ideal, prime ideal, and also I had discussed what is relation in this ideal. Always Euclidean ideal imply P.I.D, P.I.D imply U.F.D, U.F.D imply integral domain imply commutative ring with unity. This is also implied in my previous video. I had discussed this part elaborately. Today I will discuss some question about this topic. So at first I will highly recommend you please see my previous video. I have given some link in description box. But see, if you see the playlist of my ring theory, then you will understand in better way which topic you don't see. Okay? At first see those video. Okay? Let's see. First question. First question, which had come June 2016 exam in CSIR NET. The question is RBA commutative ring with unity. Note, R is given CRU. Then, this R is such that Rx is U.F.D. Given Rx is U.F.D. Unique factorization domain. Denote the ideal X of Rx by I. Then pick out the correct statement. Option 1, I is the prime ideal. Option 2, I is maximal. Then Rx is P.I.D. Option 3, if Rx is a integral domain, then I is a maximal ideal. Option 4, if Rx is P.I.D, then it is a Euclidean domain. That means this is ED. At first, I will highly recommend you please try to ownself this question. This question is very conceptual. If you can do solve this question ownself, then your all idea would be more clear. Then see my video. Okay? Let me solve the question. Here given R is CRU and Rx is U.F.D. and denote the ideal X of Rx. So, consider a ring homeomorphism from Rx to R. Because here given R is commutative ring with unity such that Rx is U.F.D. and the ideal is ideal generated by X. For this ideal, consider the mapping is such type f of px equal to p0. Obviously this is ring homeomorphism and also this mapping is onto mapping because consider arbitrary R belongs to real number such that f of px equal to R, where px equal to just constant polynomial. This is just constant polynomial. Since arbitrary R belongs to real number, f of px equal to this constant polynomial, this R, where px is the px equal to R means constant polynomial. So obviously f of px would be, or since here f of px equal to p0, so f of px equal to R, and this is true for any arbitrary R belongs to real number. So this mapping is onto mapping. Now let's see the kernel. Kernel is look like X belongs to Px such that f of px equal to 0 polynomial. And this is true only this polynomial whose constant term is 0. This is means ideal generated by x, which is equal to x times px such that px belongs to Rx. That means look at the ideal. This ideal is x times a0 plus a1x up to an x to the power n, where this ai belongs to real number. I hope my all viewers have understood clearly this ring homomorphism. This ring homomorphism is onto ring homomorphism whose kernel is ideal generated by x. Therefore, by ring homomorphism theorem, Rx modulo ideal generated by x is isomorphic to R. Have you understood? Rx is U.F.D. We all of us know this result. If Rx is U.F.D. then U.F.D. then this condition is if and only if condition R is a U.F.D. We all of us know in Euclidean ideal domain in P.I.D. if R is a field, then if and only if condition Rx is Euclidean domain, also Rx is P.I.D. Okay? Since Rx modulo x is isomorphic to R and given R is U.F.D., that imply also R is a U.F.D. Given Rx is U.F.D., so that imply R is U.F.D. Since R is U.F.D., that means U.F.D. always imply this is integral domain. So this is integral domain. And we all of us know in CRU, if Rx modulo I is isomorphic to any field, then I is maximal and Rx modulo I is isomorphic to this if I integral domain, then obviously I is prime ideal. Since R is U.F.D., that means this implies this is integral domain, so obviously this I means this kernel, obviously this is prime ideal. So I is a prime ideal. Second option, if I is a maximal, if this is maximal, then Rx is P.I.D. Notice, if this is maximal, if I is maximal, that means this is isomorphic to field. That means this R is now field. If R is a field, notice these properties. If R is a field, then Rx always integral domain, Euclidean domain, and Euclidean domain imply Rx always P.I.D. That means Rx is P.I.D. So by this, option 2 also right option. Option 3 imply if Rx is integral domain, then I is a maximal ideal. At first thing, if R is a field, then Rx is Euclidean domain. Even Rx is integral domain, that imply always R is a field. And if R is a field, then obviously this ideal is maximal ideal. So option 3 also right option. And option 4 imply if Rx is PID. Rx is PID means obviously these R is a field. Then it is a Euclidean domain. Rx is PID means this is R is always field, and field imply all field is Euclidean domain, we all of us know. So option 4 also right option. That means here option 1, option 2, option 3, option 4 both are right. I hope my all viewers have understood this question easily. Okay? Oh well. Next question, which had come CSIR NET December 2016 question. The question is option 1 ZX is PID, option 2 ZXY modulo ideal generated by Y plus 1 is U.F.D. Option 3 if R is PID and P is a non-zero prime ideal, then R mod P has finitely many prime ideals. Option 4 if R is a PID, then any subring containing 1 is PID. We all of us know ZX is not PID because PID means it contains only single ideal, but ZX contain ideal generated by x comma 2, which is not single element. Here ZX comma Y modulo Y ideal generated by Y plus 1 is U.F.D. For this consider one mapping ZXY phi, consider the function is phi, ZXY to ZX, such that PXY map to, since here ZXY divided by ideal generated by Y plus 1, so PXY map to PX comma minus 1. Okay? This is onto homeomorphism because consider QX belongs to ZX and PXY equal to QX times minus Y, then phi of PXY always map to QX times here minus 1 minus 1. Therefore, phi of PXY equal to QX. So, this mapping, this ring homeomorphism is onto homeomorphism. Therefore, here the kernel is, phi is those PXY such that P of x comma minus 1 equal to 0. And this is actually equal to ZXY times Y plus 1. Y plus 1. Because here P of xy equal to P times x minus 1. If you put y equal to minus 1, then this value would be 0. And this is nothing but ideal generated by y plus 1. So, ZXY ideal generated by y plus 1. Since this is the onto homeomorphism, so this is isomorphic to ZX. I hope my all viewers have understood. That means since we all of us know if ZX is U.F.D, means if Rx is U.F.D, then that imply R is U.F.D. We all of us know Z is a U.F.D. So ZX obviously U.F.D. So Option 2 is a right option. Option 3, if R is P.I.D. and P is non-zero prime ideal, then R mod P is a finitely many prime ideals. We all of us know in P.I.D. every non-zero prime ideal is a maximal ideal. Since R is a P.I.D. and P is non-zero prime ideal, then R mod P has finitely many prime ideals. For this, since R is a given P.I.D, so in P.I.D, every non-zero prime ideal is maximal ideal. So if P is a maximal, then R mod P is isomorphic to field. And in field, always two ideal exist, zero ideal and ring itself. And only prime ideal is zero ideal. Zero ideal is only prime ideal. So R mod P has finitely many prime ideals. This is right option. Option 4. If R is a P.I.D, then any subring containing 1 is a P.I.D. First no. If Q is a field, then Qx is a P.I.D. Qx is a P.I.D. which contain Zx, but Zx is not P.I.D. So option 4, this is not true. Only option 2 and option 3 is the right option. I hope my all viewers have understood clearly. Okay, well. Today I will stop here. In my next video I will also define this type of question about prime ideal, maximal ideal, U.F.D, P.I.D, integral domain. Actually this type of question very important for any competitive exam. Okay, see you so soon. Stay safe and stay positive. And don't forget to subscribe my channel for more videos. Thank you so much.